it's not recorded yet. So let me push on hold. Okay, it's recording now. Thank you, Jenna. Then it's not right there. So it's actually here, right here. You do have, some people have question right here. Okay. So let me sort of talk about it a bit. So again, it's coming from right here. It's okay. Your homework as well. We are looking for the CDF as a pivot. Then we are looking for decreasing function. I think I've been saying many times right now, it's a decreasing function of theta. And then you do have in there alpha 1, alpha 2, alpha 1, and then 1 minus alpha 2. Basically, it's quantile to quantile, A to B. So pivot. Then again, it's you're using it's what, lower bound to find upper bound of the interval, upper value to find lower bound. Basically, that's where these two equations come from. Okay, so right here is actually the same thing right here. Okay, I do know that I need to using alpha 1 right here to find upper bound, which is theta plug-in ut. Okay, so if you're coming back to this right here, okay, I just write down that after we finish discussion. Oh no, it's lower bound. Sorry about that. So I'm talking about upper bound first. So let's go here. Upper bound right here first. Okay. So we are using lower value alpha 1 to find upper bound of 95% of 1 minus alpha constant for theta. Okay. Really is you plug in theta as upper bound to solving for that equation. Making sense? Which means that this is CDF, right? So right here, probability of t smaller than t, probability of t smaller than t. Plug in theta as upper bound to solving for this equation. There you go, upper bound, right? You have real alpha value right here. You have alpha value right here. Okay, you solving for the upper bound of theta, which means that it's by by definition of CDF, right? It's integral from what? From theta right here. Because the 12 right here is what? It's from mu smaller than y to infinity. That's a range of y is. And then we need to plug in theta as the upper bound. The reason why right here you will see un, right here you will see u, y right here. Because theta got to be replaced by uy, and the range of y coming from mu to infinity. So it means the lower bound of the theta need to replacing by u theta, the ux, the reason why for uy right here. Making sense? And then up to what? Up to y because you do have t smaller than t. Okay, the inside guide would be PDF. Okay, good. The same thing right here as well. You actually using alpha 2 right here, but I writing down t bigger than t. Okay, so really nothing but what? You actually is 1 minus alpha 2, then t smaller than t, either way, right? So again, CDF right here, value is 1 minus alpha 2. Okay, 1 minus alpha 2. Again, keep in mind, you to solving theta plug-in lower bound, then solving for lower bound x. That's what this equation means, right? Okay. Again, is theta plug-in to lower bound, and then CDF probability is smaller than t, big capital T smaller than small t, become 1 minus alpha 2. The reason you use alpha 2 right here is I have in that bigger one. Let me write it again. Let me emphasize that again. The reason you see alpha 2 right here It's because I write bigger than t, okay? Then actually it's coming from t smaller than t, 1 minus alpha 2, okay? Then again, if I using that alpha 2 right here, t bigger than t, right here, it's nothing but what? From t to infinity, because the range of y goes to infinity, okay? And reason why this is y is infinity, then alpha divided by 2x, okay, or alpha 2 right here, it's okay. Then could you actually using this guy right here? Let me write it here. So although I write so let me point out right here, this guy coming from this, okay? But could I actually write probability t smaller than t, given their theta is LT equals to 1 alpha divided by 2? Yes, it's really nothing but what? Integrating again, this guy smaller than t, upper bound is t, okay? And then lower bound right here, we're coming from lower bound right here. Then inside guy is PDF theta, then dt equals to 1 minus alpha 2. You can write out as well to solving for lower bound, either way. Okay, good. That's the reason why, although this guy right here looks confusing, but actually it's not, as long as you follow the definition of a PCDF. And then remember that it's solving for lower bound, upper bound, actually replacing what theta as lower bound, upper bound is to solving for their solution. Okay, good. So if you still have a question on this, we can talk about that, because I do want to move our final pieces. Okay, so let me go to my file. Where is my file then? Okay, my file is right here. I think right here. Okay, good. Let me go through this large sample ML based methods. Okay, you can see number 1 right here. The reason this number 1 right here, of course, the number 2. Okay, with more complicated large sample theory of MLE. Okay, so this chapter actually is much useful in the future, I think, especially if you want to develop a new methodology, with new methods, or you are dealing with totally new questions. Then the first estimator, in case you need to looking for estimations, the first estimator in your mind would be always MLE. Okay, the reason for that is MLE do having a lot of good properties along the way. You can see that. Then especially the large sample theory of MLE is established. Okay, of course of course you might dealing with really totally new kind of estimators, and you are trying to deriving the properties, the properties of estimators. That could be possible. But if in terms of practical point of view, say if you only get a quick method, then MLE should always be on your mind. Okay, again, sometimes may not be easy to write it down as MLE, again, because of intractable things. Okay, so that coming from Kassenberger, chapter number 10. Okay, before I went into the details, I do want to have in some notations. You actually see that before, when we deriving Cramer lower bound. Okay, so first one is x1 to xn is ID. I want to main point this out. Okay, so the results right here, okay, it looks like many apply to ID data, but it could be generalized to non-ID data. Most likely it's independent but not identical. For example, regression problems, you saw meter number 2, it's in a Poisson count. Okay, good. Okay, hold on a bit. So let me talk about meter number 2. So I actually posted that in the Sakai. You see that, I see that, right? So I don't want to spend time to go through the solutions, okay, because I do want to preserve 2 lectures, mainly talking about large sample properties MLE. So in case you don't understand what I write in your paper, or you feel like you don't get the answers, I post solution key on Sakai already, so you can download it, look through it. If you, in case you don't know how I get that answers, let me know. Okay. So we can having different time to talk about it. Okay, to go through the solution key with you, to sort of communicate a bit about what solution is. Okay, good. So like method number 2 is it's identical, it's independent but not identical. Then in that case, the results really just slightly adjust to the results I written down right here for ID data. Okay, I could show you after these 2 lectures, and I think you possibly will see that occur in the final as well. Okay, so in the past final exams, okay, then I'm going to post the past final exams on Thursday, and we are talking about the questions on the next Monday in the discussion section time. Okay, then I think the semester formally ends this week. So I'm going to spend more time on next Monday to go through more questions, spend about 2 hours to go through our past exam questions. Okay, so that won't be identical to the regular Monday discussion section in about 1 hour. Good. Okay, coming back to this. Okay, so right now it's MLE deriving from log local function. Okay, so right now to write down log local function with my friend summation I from 1 to n, which means that I want to write everything as log local function, a summation I from 1 to n. The inside guy for each guy as li, which means that it's really nothing but log PDF, and then with only single observation. Okay, then I told you what score function is. You take the first derivative to the log local function, and then again I'm going to write down everything inside summation I from 1 to n individually as a ui. Okay, score function. Then I said if you keep taking differentiation, the second derivative of the log local function will become observed information, but don't forget about -10 right here. Keep that thing in mind. When I say observe information, then I do including negative 10 right here when you do like a second derivative of the log local function. Okay, then by notation inside guy become ji. Okay, whole thing as a j theta. Good. Really here is nothing but writing down log local function, score function, observe information in terms of your friends summation I from 1 to n. Okay, good. And then going further is what? You taking expected value on the individual observed information that become expected information. Okay, then right here, I do want to point out one thing is the so-called I1 right here. This one actually coming from what? Individual expectation of JIs. Okay, and then because ID structure, so every information expected value is the same. Now how to imagine, right? Like every individual's means the same. So that means if I'm talking about so-called expected information from the NID sample, it's actually n times I1. Okay, that means it's accumulation of the information from NID subjects. Okay, now how to see that. Okay, but right here, I do want to point out is notation difference. IM means total information coming from an individual. I1 is information only coming from one individual. Okay, so if I can write something like here, right? If I can write something like here, okay, so not surprising to see that what? Li right here is a function of xi. which means that if you willing to say, even though I write it here, right? So each guy are function of x1 to xn is, okay? Although I say like a function is collecting the data x1, little x1 to little xn, then to do inference on theta. But imagine that if you can repeat it multiple times, then your little xi become capital Xi, then become random variable. That means inside guy right here could become random variable. And then each log level function become ID data because they are all function of x1 to xn. Okay, good. So that means I can treat like a function as a function of the random variable itself. Okay, x1 to xn. The same thing right here as well as u1 to un, also a function of x1 to xn. Okay, good. Good. So that means u1 to un also random variable as well. And then we actually talk about it when we talk about Kramer-Robin. We talk about CRLB, right? Number one, it's mean 0, then variance it's I1 theta. Not hard to derive in that at all. For example, right here it's expected of UI, mean of U1, okay? And you know that already, right? I keep saying so when we talk about CRLB, okay? That's exactly the derivation of U score function H, right? This is definition of score function U1 H, okay? And then this guy nothing but what? Writing down your LI become log PDF, okay? Also by definition. And then doing so by partial theta on log fxi, nothing but what? You taking your 1 over fxi, because the log function right here, right? You do differentiation on log function. The first one is inverse, right? Become 1 over fx. Then your numerator it become what? Become partial theta, then f. Okay? Just by definition of differentiation on theta. And then by doing so, then if you really write down so-called expectation right here, expectation right here, expectation nothing means what? Integral, right? So nothing but what? Equals, I do have integral from sample space. Then I do have my inside guy is something as a quantity you are trying to take expectation with, okay? Then times what? By definition of expectation, nothing but times PDF, right? Okay, and then these two guys are cancel out, then become this equation. Inside guy integral become partial theta, then fx, then theta, then dx. Okay, then remember we talk about integral on sample space, differentiation on permanent space. Then I can switch, right? So-called exchangeable property, which means that we do need to have in that condition to be satisfied. Integral and the differentiation could switch. Then x become beta will be dd theta, actually. And then inside guy become integral dd theta, integral sample space, PDF theta, then dx. And that means what? This guy integral over sample space of PDF, nothing but 1. And then dd theta 1 becomes 0. So that means expected value of UI is 0. Then how about variance then? How do I know variance is actually is I1 theta? Okay, so that one in detail in the exercise 7.33 in Kasselberger. Okay, you can check it through. I put some outlines right here. It's not hard to prove, but it's easier to go backwards. Okay, so if you're trying to get if you try to get started from reference UI, you possibly got stuck a little bit. Okay, not easy to straightforward to see that. Reference UI equals to I. We're going to do backwards. That means I showing I1 theta equals variance of UI. Then it'll be much easier. This is outline or proof. Again, it's by definition of I1 theta right here, right? By definition, expected value of observed information. Observed information is nothing but negative of second derivative of log-like function, right? Okay, then moving forward right here is what? Nothing but taking your second derivative become your separate derivatives. You do first derivative, then do second derivative. Okay, straightforward. And then if we redo first derivative inside, then again become what? Become right here, right? First derivative on log function, nothing but taking inverse, then taking partial theta in your numerators. Okay, good. And then this equation become much trickier. Okay, so right here is what? Imagine right here, I can put it on the side, I can have a space right here. So imagine what this means. You are doing partial theta on some function, right? It look that way. That function have a numerator, a denominator. Okay, and then what does that mean? That means you can actually do what? You can actually do what the calculus teach you. You can actually do what you learn from calculus in high school, right? I do some partial on the ratio, which means inside guy say expected value right here. Inside guy become what? Okay, it's up to you about the formula you remember in high school, how to do ratio in the partial, right? So I do this, right? You're taking square on your denominator. So let me put, and then have what? You put partial theta. I think I'll put the first, do the numerator, it's then times denominator. Okay, then minus what? Minus, you do numerator again, partial theta. Oh no, it's not. So you do your, hold on. Okay, then you keep your numerator and do your denominators. Okay, that's how I keep in mind from high school. So then you're taking out all this because they're identical. So you can always feel put to square right here. Okay, and you will find out that this is a minus. This is minus become plus. Then this guy exactly, this part exactly what your answer is, right? Which means that your first part, expected value of partial square, partial theta, f of xi theta, okay? Right here, divided by, remember right here you have fx1, fxi, cancel out. So that means your denominator only have single xi, single f of xi right here. Okay, and then you are going to do your best to show this guy is 0, right? So to get to here, okay, good. Then why that's 0 then? It's actually not really hard to show that. Again, you're going to using expected value, then become simple space. Then whole thing inside, you write down that. Right, second derivative, that's the quantity you're looking for. Hold on, I got some issue of my power. Okay, coming back. Okay, then what? Because expectation, you put that inside random variable times your PDF, right? Again, this guy taking out. Okay, then because I don't have space, so let me do this. Okay, maybe I can still survive, I think. So partial square, partial theta square, then f of xi, then dxi. Okay, good. And then the next one would be, actually, it's not surprising to see you got another assumption, which basically another exchangeable assumption for you to put your second derivative dxi, which means that this is second derivative. Again, I can write down as a partial theta, then partial theta. I can put double partial theta, right? And then I can put one partial theta out because exchangeable property. Okay, and the reason I want to write that is because of what? Because I do know inside guy equals, its inside guy equals to 0. Why is the case? Exactly coming down your score function right here. Okay, I think so. Maybe right here. So let me take out everything out so you will see clearly what I meant by right here. I'm talking about right here. You guys see that? Right here, equals to 0. Okay, again, this guy right here, equals to 0 as well. Okay, so that finish your proof. You basically show that, of course, there are some way to go as well, but it should be relatively easy to see what's going on. Okay, good. Right now, if you show this equation, but what I did, and then this guy become what? This guy becomes, you could do inside guy right here becomes partial theta log f of x, right? If you do that, you do partial theta log f of x, then become inverse, then partial in the numerators. Okay, now how to see that as well. So if you don't mind, I want to take this out. Okay, so it's easy to see what happens. Oops. Hold on. Okay, I bet what happens. Okay, good. So this guy, partial theta, then log the square. And then this guy is nothing but what? This guy is nothing but, this guy, let me see. Inside guy nothing but score function, isn't it? So that means I can write actually inside guy is equals to expected value of ui, then taking square. Right? Because this guy nothing but ui, because the ui is first derivative of log f function. Then how do I comes up with the variance ui? Also straightforward, because I do know variance equals to expected value ui square minus ui, then taking square, right? And then what this term goes to? Expected ui, this guy is 0. So of course I can take everything out right here, become eui squared, then become variance ui. Okay, so that means in terms of score function, by derivation, ui right here, okay, the mean is 0. The variance ui is I1, is information number. Okay, good. Okay, So the reason I wanted to have that, as you can see later on, why do I need to know about expected value of UI, then variance of UI? Okay. Before I say so, I want to summarize its notations, right? So again, as you can say J1 to Jn, well, J1 to Jn is ID mean I1. Again, I said information I1 is expected value of Ji's, right? So it's not hard to see that as ID mean I1 theta. And then we always call I1 theta as a visual information. If you heard about that before, okay? Not only about expected information, also about visual information, but from single observation right here. Okay, then we call this information number, okay? And then IN again, I want to mention that IN theta is n times I1 theta. It's okay, n times because accumulation of n individual observation. Okay, good. So then this little example right here to show that, okay, how do I deriving each individual logical function, score function, and then observe information? Really nothing but writing down your ML. Really nothing but trying to show what ML is. Okay, so for example, right here, I'm trying to derive in the left-hand side as a ball. So let me save something first. So x1 to xn. Okay, I want to write it. I want to save it. Okay, good. I want to save it. So right here is x1 to xn is Bernoulli theta. Okay, then theta is from 0 to 1 right here. And then by doing so, you could write down Lagu function, right? Lagu function. So let me put that as right. F Lagu function, nothing but ID consecutive product of the single individual PDF. Right. And then I have 1 to n.
So yeah, that is
Okay. So then based on the Bernoulli, PDF Bernoulli is what? So theta, then xi theta, theta xi, theta xi. Yeah. I was confused about which one is in the power side. So join PDF of the Bernoulli. And then the same thing when you're deriving MLE, you're taking log, right? I from 1 to n. Then you have xi log theta, then plus 1 minus xi, then log 1 minus theta right here. Okay, so this guy right here is really just combine about, let me see. Then you will call that it's inside guy right here. It's Li, then theta, xi, right? Each individual Li, the whole log Lagu function is summation over Li's, right? Again, this is your friend. I from 1 to n, summation over Li right here. The reason I write it here is I want to combine of the xi's, maybe easier to derive in something later on. That means I can do this. I from 1 to n. I put xi, I have log theta, and then I have minus xi, then minus log 1 minus theta right here. Okay, then plus log. I have 1 log 1 minus 1 minus theta left. Okay, so right here, nothing but what right here, log theta over 1 minus theta. Okay, good. And then use theta nothing but take first derivative to the logical function. So that means you keep working on it. Xi differentiation log theta doing partial theta become 1 over theta. Then plus 1 minus xi, really 1 over theta. That's a partial, but keep in mind you have chain rule 1 minus theta right here. So this guy would become -1. Or you want to write down it's just taking everything right here, become negative. Okay, so I think this is sufficient. Of course, you can even simplify this guy right here. You can gather. Okay, again, sorry about that. Again, this guy is ui right here, right? U theta basically is summation I from 1 to n, ui, then theta given xi is. So inside guy is ui. Okay, of course, you can first simplify to combine together like I did right here. Nothing but combine theta and 1 minus theta. Okay, so this guy xi 1 minus theta, then minus, right? 1 minus, then minus. Yeah, I have 1 minus xi, then theta, I think. Yeah, I think so. And then inside guy, you can simplify to eventually xi minus theta. The same thing I showed you right here. Okay, purely computational, should be straightforward to handle it. Okay, then of course you can keep doing your differentiation as a second derivative. I from 1 to n. You keep doing partial, then this guy right, you keep doing partial, then become -1 theta -2, right, from first term. Then -1 minus xi. This guy right here, keep doing that, then -2x. Okay, then I said this guy right here, again, it's ji theta, then xi. Okay, then of course you can keep simplify that to combine together to become this. Really nothing but recombine. You have really eventually, oh, of course, forget about into minus term right here, become your j theta. That's critical. Otherwise, you have a negative information, which doesn't make sense at all. Okay, so that means eventually simplify to summation I from 1 to n, then xi theta square, then minus, then 1 minus xi, then 1 minus theta, then square. Okay, of course, you can keep combining theta square, 1 theta square in the denominator, and then working on numerator, you get the answer right here. Let me skip that. Okay, so that means everything, really just nothing you would do when you derive MLE. The reason I keep wanting you to do second derivative of Laplace function is exactly trying to prepare you to understand what observed information is. Okay, if you do your ML, if you rechecking your second derivative, that's more than 0, then everything will go through in this chapter because you need that every piece of the derivation when you say that it's MLE. Okay, good. So then double check on something we have been teach. Number 1 is, I said expected information is N1 theta, right? N1 nothing but taking expectation on the J1 is or Ji is. If you go back to Ji right here, okay, if you take expectation, then everything is easy because, oh, not necessarily easy. You do have kind of, xi, I think xi or xi square. Oh, it should be xi. Then it's xi is easy then. I thought it's xi square. Okay, good. Then you do that, then basically it's what? Theta square 1 minus theta square. You're taking expectation on this guy right here, nothing but linear, right? EXI becomes theta. Okay, let me just jump a little bit. This guy actually EXI, right? EXI, I just write theta directly. Then minus 2 theta square, okay? Then because EXI is theta times theta is theta square, 2 theta square. Then plus theta square right here. Okay, so that means I could simplify to what? Theta, then becomes theta, then minus theta squared, right? Okay, so this guy becomes theta times theta squared, this guy theta, then times 1 minus theta. Then cancel out of this guy right here, become 1 theta, 1 minus theta. It's exactly what's going on right here. So that means expected, so that means information number for Bernoulli case is 1 divided by theta times 1 minus theta. And then looking at this, number one, I say score function. Expected value of score function is 0. How do I see it? This is UI, right? You take expectation on the UI. What happens? You take expectation right here. Right here. What happens become what? Theta times 1 with theta. You take it out, right? You take it out of right here because it has nothing to do with the expectation because constant. Then in the numerator is what? EX1 minus theta. Then EXI is theta because Bernoulli. Then theta minus theta, this guy becomes 0. No kidding. Exactly what I said. It's expected value of score function is 0. Then how about variance? You could do the same thing, right? You could do variance right here. And then you do know your score function is xi minus theta, right here, right here. Okay. You do know that score function UI is xi minus theta divided by theta times 1 minus theta. You're deriving variance, right? It should be easy for you right now. Is what? You do have a constant. You're taking out variance. You're taking square, right? You're taking the constant out of variance. You're taking square. The inside guy become variance xi minus theta. Then you also know that this guy is nothing but variance xi. Minus theta doesn't matter because minus constants. And then remember, what is the variance xi in terms of Bernoulli? E equals theta times 1 minus theta, right? That's what variance of a Bernoulli distribution is. So what does that mean? That means I can have cancel out, eventually say 1 over theta times 1 minus theta. This guy exactly equals to what? I1 theta is. So no kidding, that means what we derive is actually true stance for Bernoulli case. Again, expected value of UI is 0. Variance of UI is information number. Why do I do that? That's exactly the starting point. Trying to derive large sample property of MLE. Before doing that, I'm going to doing derivation of the large sample property of score function. Again, I'm writing down score function theta 0 as a summation I from n as a UI theta 0. It's okay. So let me just saving some space. I don't want to everything condition xi. So let me take this out, but you do know what I mean by right here. I want to write here. Okay, good. So I said summation I from 1 to I is your friend. Okay, this guy ui theta, nothing but function of I. Ui itself also random variable as well. Okay, so if we look at u theta, you could imagine it's nothing but summation I from 1 to n xi, for example. If you do so, then remember I can freely using what? Large sample theory. I'm sorry, central limit theory. Okay, of the X bars. Remember that? So I said central limit theory is what? For X bars, root n X bar minus expectation X1 goes to D, then no more than 0, then variance of X1. This is the central limit theory. You imagine your U theta is something like X bar. Okay? use summation I from 1 to n as a ui as a random variable. That means I can also write the central limit theory version of a ui theta by doing that 1 over n u theta right here. Or maybe I can write down summation I from 1 to n, summation I from 1 to n, then ui theta 0, right? This got nothing but u theta, right? Okay, I purposely write so I'm creating x bars. Okay, I'm creating this guy holding the u bar, for example. Okay, then by central limit theory, it minus EU1, right? Okay, the same thing right here. Okay, then goes to D, then normality, then 0, then variance of U1, isn't it? Just by central limit theory. And then what does EU1 is? What EU1 is? Nothing but 0. Again, I say score function, expected value of score function is 0. Okay, then what is variance U1? Right here, right? Variance U1 is I1, information number. So no wonder whole thing's nothing but central limit theory. Central limit theory. Okay, so then root n times 1 over n become 1 over square root n, and then u theta, and then 0 is 0 gone, so 1 over square root n u theta, then goes to d, then normal 0 I1 theta 0 x. Okay, nothing but central limit theory. That's the first result we're gonna get. Okay, then this guy right here, not surprisingly, what theory I'm going to use, right? So again, if you look at j theta 0, nothing but summation I from 1 to n, then ji theta 0. Okay, if you're really writing down 1 over j theta, really nothing but 1 over n summation I from 1 to n ji theta 0, right? Again, the whole thing, right? Look like what? J bar, isn't it? Right? Whole thing is summation I from 1 to n ji divided by n, nothing but bars. Okay? If it's nothing but bars, then what if I write here goes to P expected value of J1. What theory I'm using? Nothing but weak law of large number. Okay, and then by definition, expected value of J1, nothing but equals to I1, then theta 0 as an information number. That's why you will see that result right here. Okay, so really the result nothing but based on what? Nothing but based on weak law of large number. You can get a result. Okay, third one is for K function. K function actually is taking a third derivative of the logical function. Okay, just by definition. But again, something that right here, right? Also some bars. This guy become K bar. K bar then become expected value of the K1s. Okay, I don't know what a K1 is. I don't know what expected value of K1 is, but it's fine. By notation, I can write so. Okay. Later on, we will be able to use their results. Okay, good. So far so good up to this stage. Any question at all? So if not, then I'm going to move on the formal large sample property of MLE. Okay, good. So there are two important conclusions about MLEs. The first one called consistency. Consistent means that my MLE theta hat is going to converge in probability to theta 0. It's called consistency. I said that before in class. Okay, good. I'm not going to show that. I'm not going to show right here. It's taking much longer way to show why theta hat is consistency estimator of your parameters. Okay, it relies on other theories to support that. I'm not going to show that theories right here, but keep in mind it's MLE is always consistent to parameters that you are interested. Okay, and then but large sample normality would be possibly much easier to show. And then using everything you learned from previous slides, you would have their results. Okay, so right here it's MLE is asymptotic normal. Okay, by writing so, you have a root n theta MLE consistent estimator of theta 0. It goes to D. That means when n is large enough, or when n goes to infinity, MLE is going to distribute the TX. Okay, normality, good. Then what's the mean of normality then? The mean of normality is 0. Not surprising to see, right? Because theta hat is a consistent estimator of theta 0. So it means when n goes to infinity, theta hat is still going to be close to theta 0. So no wonder the mean is 0. Not surprised to see. But what is the variance? Okay, keep in mind a variance is nothing but taking the information number, then taking inverse. Don't forget about that, which means that it's asymptotically MLE's distribution is going to become normality. Mean 0, the variance is the inverse of official information. Okay, don't forget about inverse of official information. Why this guy is actually inversed in some sense then? Okay, so statistics code information, or maybe computer scientists code information, that's for reason, right? So imagine it's whenever you're having more information. Okay, what does that mean? You have clear picture about theta 0, right? Okay, clear picture also means that you have less variation. Okay, you're around the theta 0 a lot, and then who is reasonable variation of that? So it means why the inverse term making sense? Larger information, I1 become bigger and bigger, or IN become bigger and bigger. Then you take it inverse, then your variance becomes smaller and smaller. Okay, so I always say this is something you definitely need to write in your cheat sheet. But right now you don't have a cheat sheet for finals, so this is something you need to keep in mind always. Okay, the variance is always information, then take an inverse, or say inverse of official information that we always talk about. Then where does that come from then? I only have 17 minutes left. I think it's good enough. Okay, good. It coming from it. So it coming from this. So let me just play around a bit. Coming from first one is, if I do plug in theta hat into my score function, what does that equals to? What does that equal to? Nothing but 0, right? That's how you solve for MLB, right? You're solving for, you derive your first derivative and set it as 0, and you solve it for theta hat. Okay. Again, statistics is using not typical, amazing, fantastic mathematics skills. Next one is nothing but doing what? Taylor expansion. Okay, so if I do Taylor expansion on theta 0, say right here, okay, then what's the next term? Next term, by definition, you're right. Hey, I take a prom, right? First derivative on u function, and then theta hat, and then theta 0. Okay, and you could keep writing about second derivative, right? Second derivative, then 2 square, then theta hat minus theta 0, then taking square. Okay, and then dot dot dot, right? Dot dot dot. Okay, so I said if you would like to say whole thing is remaining terms, okay, their approximation remains small in some way. If you would like to say so, if I think about that way, then I can write down something theta hat minus theta 0 right here in my left hand side. And then I'm going to move everything right here to the left hand side. Okay, become what? It's got become, I do have 1 minus u theta 0, right? I'm moving u theta 0 in the left hand side, become minus u theta 0. And also mu prime theta 0, then taking inverse, right? Okay, good. And then of course I have a bunch of remaining terms right here again. Okay, I just remaining terms right here again. My talk is actually putting down as root n theta hat minus theta 0, right? Times root n. And then I purpose writing down something. First one is u want u prime. Whoops, where does that go? Okay, u prime right here is what? Okay, let me put it here. U prime is first derivative of score function, nothing but what? Observed information matrix. So that means I have minus, I have u prime right here. That means this is nothing but j theta 0, then inverse. Making sense? Okay. And then I also have a u function theta 0 right here. Okay. And then plus root n times Rn. Okay. Of course, find out root n right here. Okay, good. And if I purpose writing down, I do need to go back to, okay. If I purpose writing down square root n u theta right here, okay, that means I can write down, let me jump a little bit to see if you agree. Okay, so right here is what? 1 over n inverse, see right here, 1 over n inverse become n times 1 over square root n become square root n. Okay, so nothing changes. Okay, okay, square root n Rm right here. Okay, say right now if n goes to infinity, okay, Feng-Chang are looking for what? Looking for less, right? Looking for less. Eventually n goes to infinity. Say if we write down right here, if you would like to say, well, I'm not going to get into details, but if you okay with that, say if this guy goes to 0, right? Because remaining term is so small, and then even the times root n, but because you know, for example, we always talk about is converge quicker than root n, something like that. So if you willing to support, this guy goes to p, goes to 0. Okay, then what happens to this guy? Remember I talk about right here. Okay, right here. Right here. Okay, 1 over square root n times u theta. This guy goes to what? This guy goes to d, then normal, then 0, then I1 theta 0. It's not inverse. I1 theta 0. Okay, then how about this guy then? 1 over n j theta right here. It was this guy goes to p, inside guy goes to p, then I1, then don't forget about inverse. Making sense? Okay. Goes to B, goes to N, goes to P. Eventually goes to where? Eventually goes to distribution, right? What theory I'm using? Slavsky. Okay. Then become what? I do have N, then 0. Okay. I do have I1 right here, inverse. If I put inside the variance, become what? Become square, right? Yeah, become square. And then I1 inverse 2, then comes I1 theta 0, then eventually become theta 0. I1 inverse theta 0. So right here become inverse 1x. Okay, so you get results. Easy. Nothing but using large sample properties of score function and using weak low large number of the observed information. So that means MLE of theta 0, this guy is not hard to derive. Not using nothing but what? Tail expansion. But you do need to know about how to operate on the score function. U theta has a 0h. Okay. So again, MLE consistent estimators, then asymptotic normal, and the variance. Don't forget root n right here, and then variance right here. Okay. And then sometimes imagine that it's not necessary you are going to using theta hat to do the parameter of interest. It's not necessary theta hat, but not necessary theta 0. What if the parameters of interest is actually tau theta 0? You see that before, right? Where did you see that? Meter number 2, right? I'm not necessarily interested on theta. I'm interested in exponential minus theta. In that case, then the parameter of interest is a function of theta 0. Then what is MLE for that function of theta 0? It's nothing but function of theta hat MLE based on what property? I guess you guys all know that, because I don't see any single person fail on the question in meter number. I don't see any single person fails on that meter number 2 questions, right? So the MLE by invariance of property, tau theta hat would be MLE for tau theta 0. Okay, so that means, of course, it's consistency. Okay, then not only about consistency, can I actually deriving the large sample normality? Also easy, right? From here to here. What method I'm using? Nothing but delta method, right? Okay, I apply G function on theta hat, become G theta hat right here. Well, right now G function become tau function. I apply tau function on theta hat, then minus tau function apply theta 0, and the variance coming down to here. Become what? By delta method, it's G prime theta 0 squared. Remember that? G prime theta 0 square, then times the variance of their quantity, right? So that means nothing but right here, right? G function right now is my tau function, then tau prime theta 0 taking square, then times the variance. Variance is I1 inverse, then become pretty bigger. Okay, then become right here. Okay, so did you see this guy before? Let me take out everything right here. Did you see this guy before? This guy, nothing but Clear-Mao lower bound. Remember that? From bios661 meters. Okay, except that I put root n right here. Then if you actually put down inside guy, this guy nothing but what? M right here. Okay, good. So that means, did I talk about it? I think so, right here. Okay, which means that that's asymptotically why MLE is so popular, because we do think as long as condition satisfy, actually it's a mild condition satisfy, then when n goes to infinity, the MLE is going to become asymptotically efficient, which means the variance of MLE is going to reach in the lower bound of CILB of MV unbiased estimators. Okay, good. Although sometimes theta itself is not unbiased, but it's okay. As long as n goes to infinity, the variance of MLE is going to be that small than beating out a bunch of unbiased estimators. Good. Okay. So then, talking about efficiency. Okay. Really nothing efficiency, nothing really compare the variance or compare the bias. Okay, or compare mean square error called relative efficiency. Then sometimes when we talk about asymptotic relative efficiency, asymptotic sometimes, also, I mean, not say sometimes, we always compare with what? Unbiased estimators. Consistent estimators. Okay, so for example, one consistent estimator T1n having that sigma 1 square as a limiting variance. And then T2n, another consistent estimator, have a limiting variance as a sigma square 2. Okay. Then asymptotic relative efficient, or called ARE, right here, is really nothing but taking ratio of a variance. Because both are consistent, so in terms of sense of bias is small, right? So there's really nothing to compare with the bias terms. Then what's the remaining? Remaining is which one have a smaller variance. Okay. So then right here, because you put your comparison in a denominator, it's, or maybe I don't know, it's depending on, so relative. So I was confused about which one is denominator, which one is numerator. So I think right here, if you had T1 with respect to T2, then that basically means this is your target, this is your control edge, this is your kind of reference group. Then you put your reference group in the numerator, your estimator put in the denominator. So basically means that you're looking for something. You want your variation smaller. So you're looking for it. You have higher ARE bigger than 1x, because you want to have smaller variance compared to some reference one. Okay. So that means ARE bigger than 1 is good estimator. Okay. Final 3 minutes. I think this one is easy to go through. So let me go through it. So we can talk about asymptotic distribution of LRT next time. Okay. So right here, if x1 to xn from the logistic regression, I mean, is that from logistic distribution data, you check your Kassenberger, you'll find what the form of logistic distribution is theta. Okay, so you'll find out its expected value is theta. Then variance is a pi squared divided by 3. And then the first one, I'm using X bar right here. So that means this guy is based on what? Central limit theory. Okay, if based on central limit theory, then this guy is expected value of x1 ex1 it's, and this guy is variance x1. So no wonder this guy is theta, this guy is pi squared divided by 3. That's right here. Okay, then if I base on the MLE, if I writing down theta MLE, although I don't know what theta had look like, okay, you actually don't have to solve it in this case. The reason I say so is based on the property of MLE, I do know this guy is root n theta hat minus theta. This guy nothing but I1 inverse theta, right? Remember that? So that means although I don't know about what theta height actually look like, I can still writing down the variance. The best I can do is deriving the I1 theta by definition right here. Okay, that means you find out what PDF of logistic regression is, then taking log, taking second derivative, and taking expectation, then taking minus. You will find eventually, amazingly, is 1/3x. Okay, then you do then you do your inverse. Then right here becomes 3. Taking inverse becomes 3. So it means I do have 2 estimators. Both are consistent estimators. One X bar, one theta hat. And then they do have different variation. Okay, then ARE basically means what is X bar to theta hat. And then you put this guy's 3 variance of the MLE, this guy's variance of X bar. It turns out to be 0.91, which basically means that what? MLE is a beta estimator because 3 is more than pi squared divided by 3x. Okay, again showing that it's MLE is going to be asymptotically most efficient estimators. They're going to have the smallest variance when it goes to infinity. Okay, I'm going to stop right here. It's 1:46 right now.